Welcome to the 36th lecture of the MOOC on parallel algorithms. In the previous lecture, we found that the circuit value problem is P-complete for NC reductions. We did this by showing that an arbitrary language of the class P can be NC reduced to the circuit value problem. Today we shall see that another problem, namely the ordered DFS problem, is P-complete for NC reductions. First, let us define the problem. The ordered DFS problem is a decision problem. It is defined thus: given a graph G equal to VE, where V is the vertex set and E is the edge set, specified by a fixed adjacency list and three particular vertices S, U and V of the graph, is U visited before V in a DFS of G starting at S. This is the question that we have to answer. We are given a graph. The graph is specified using a particular adjacency list. We know that the choice of the adjacency list representation will decide the order in which the vertices are visited in a DFS. So, given this adjacency list representation and three particular vertices S, U, V, you have to decide whether U is visited before V in a DFS which begins at S. So, this is the decision problem at hand. We want to show that the ordered DFS problem is P-complete for NC reductions. Proving this, as we know, involves two steps. First of all, we have to show that the ordered DFS problem belongs to P. But this is easy to show. You are familiar with the DFS algorithm. You start DFS at S if U is visited before V, say yes, else say no. We know that DFS on a graph of n vertices and m edges will run in order of n plus m time. The number of edges in the graph is at most order of n squared. So, this is a polynomial time algorithm. Therefore, ODFS belongs to P. So, this is the first part of the proof. The second part of the proof involves saying that ODFS is at least as hard as CVP. In fact, we shall consider a variant of CVP. We shall consider what is called NOR CVP. That is, we shall show that ODFS is at least as hard from the perspective of NC reductions as NOR CVP, or we shall show that NOR CVP is NC reducible to ODFS. This will be the second part of the proof. Combining the two proofs, we would have established that ODFS is P-complete for NC reductions. Now, what is NOR CVP? NOR CVP is a variant of CVP. So, in this case, we are given a circuit as in CVP. The circuit consists of a sequence of gates where each GI is either signal 1, mind you, GI is not allowed to have a value of 0. GI is either signal 1 or GI is GJ nor GK, where J and K are less than I. So, if you are not familiar with this notation, this stands for NOR. So, that A nor B is the same as A or B negation. So, NOR CVP is an instance of this form. We are given a sequence of gates and we have to say if Gn evaluates to 1 or not. This is the question we have to answer. Now, it can be easily shown that NOR CVP is harder than CVP, or CVP is NC reducible to NOR CVP. That is because when we are given an instance of CVP, we can convert it into an instance of NOR CVP. Mind you, CVP is a general Boolean circuit, and in NOR CVP we are supposed to contain a Boolean circuit with only NOR gates. So, an instance of CVP can be converted into an instance of NOR CVP by replacing every single gate of CVP with an equivalent circuit using only NOR gates. This substitution can be done in the following manner. The negation of a signal can be achieved like this. This is an OR gate. This is because, as you can verify, the NOR of A and A is A complement. So, even if the circuit has only input values 1, we can generate the zeros that we want by negating the ones. So, zeros can be generated in this manner, and also negations can be generated in this manner using NOR gates. A or B is the same as A NOR B negation, but negation is already known to us. We know how to create negation using a NOR gate. So, A NOR B NOR A NOR B is A or B. On the other hand, A and B by De Morgan's law is the negation of A or the negation of B complemented, which is A negation NOR B negation. But A negation is A NOR A and B negation is B NOR B. So, an AND gate also can be synthesized using NOR gates. Therefore, given an instance of the circuit value problem, we can construct an equivalent instance of the NOR circuit value problem. So, that establishes that NOR CVP is P complete for NC reductions. So, this is the result we are going to use. We shall show that ODFS is NC reducible to NOR CVP. So, let us say we are given an instance of NOR CVP. So, let us say G1 through Gn is that instance, where each Gi is either signal 1 or Gj nor Gk for j and k less than I. So, the reduction is effected in this manner. We construct a graph G. The G that we are going to construct shall have subgraphs that we call G1 through Gn. So, subgraph Gi, capital Gi, shall correspond to signal Gi or the output of gate small gi, and these units in particular will have these vertices. So, if this is capital Gi, it will have a vertex named enter I and a vertex named exit I. It shall also have a vertex named S of I and a vertex named T of I. How these nodes are interconnected within capital Gi we shall see in a moment, but let us first see the overall structure of the graph. If this is Gi plus 1, Gi plus 1 will have enter I plus 1. We shall have a directed connection from exit of I to enter of I plus 1. There shall be a connection of this form. Similarly, enter I will have an edge coming into it from enter I minus 1, exit I minus 1. Exit I minus 1 will belong to the subgraph Gi minus 1. Of course, the first subgraph, which is G1, shall correspond to input G1. It will have a vertex called exit 1, which connects to enter 2. It will also have a vertex called enter 1, but there will be no edge coming into enter 1. That is because there is no unit before this. Similarly, the last unit will be a subgraph called Gn. This will have a vertex called exit n with no out degree. Exit n will not be connected to any other vertex, that is because Gn is the last unit. Now, here there will be two particular vertices, S of n and T of n. exit 1 will be connected to exit 2, exit I plus 1 will be connected to enter I plus 2. Similarly, enter n will be receiving an edge from exit n minus 1 and so on. So, apart from these connections that are shown in blue, there will also be some edges, some vertices that are common to multiple components. So, these components would interact even in some other ways. All that will become clear once I show how these components are designed. Now, let us see how these components are designed. If Gi is an input, of course, signal 1, every input is of value 1, then Gi is going to be a subgraph of this form. This is the vertex called enter I. This vertex is named S of I, and this vertex is named T of I, and this is the vertex named exit of I. Now, we have some vertices here which shall be named IA1, IA2 and so on. Here we assume that A1 through AK are the gates, or strictly speaking I should say GA1 through GAK. So, A1 through AK are the indices of these gates, GA1 through GAK are the gates that use the output of GI as an input. If GI is, in this case GI is an input itself, therefore, these are the gates that will use GI as an input. So, this is how graph GI will look like if small gi is an input. In particular, G1 is an input, and therefore, subgraph G1 will look exactly like this with I replaced by 1. Then, if Gi happens to be, the only other possibility for Gi is that it is a NOR of Gj and Gk, or let me use a different subscript, Gb1 NOR Gb2 for B1 B2 less than I. If Gi happens to be a NOR of Gb1 and Gb2, then Gi will be designed in this manner. Here we have a vertex which will be enter I, and then we have 3 vertices of this form, and we set up edges of this sort. So, exactly as in the input case, we have a connection to the exit vertex like this, but we shall also have edges of this form. So, now let me label the vertices. This is vertex enter I, this corner as before is Si, and this corner as before is Ti, and here we have exit of I. This is as before IA1, this is IA2 and so on, and this is IAK. These vertices are numbered exactly as in the previous case. This is the vertex B1I, this is the vertex B2I. So, as you can see, B1 of I belongs to GI as well as GB1. So, similarly, B2I belongs to subgraph GB2 as well as subgraph GI. So, as I said, some vertices can belong to multiple subgraphs. So, the subgraphs will interact in this manner as well. Some vertices could be common to various subgraphs. Now, there is one more piece of data to be added, which is the labels for the edges. So, first let us consider this graph and label the edges in this manner. I will put a label of 1 here and 1 here. When the label of an edge is the ordinal value of the edge within the adjacency list of the originating vertex. So, at vertex IA1, what we say is that this edge which is marked is going to be the first edge in the adjacency list of IA1. If an edge is unlabeled, it means its source vertex has only one edge and therefore this edge is labeled 1. So, every unlabeled edge by default has a label 1 and that is the only edge belonging to the adjacency list of the source vertex. For example, enter I has only one edge when Gi is an input and therefore, the edge going out of enter I is left unlabeled. Vertices IA1, IA2 etc. are going to have multiple edges incident to them. Therefore, we have to label the edge going out of it. This particular edge is labeled 1. Now, for the case where Gi happens to be the NOR of two gates, the labels would be given thus. Here we have a label of 1, here we have a label of 2 and here also we have a label of 2. These two cross edges have labels of 2 each. These edges are labeled 1, this edge is labeled 2, this is labeled 1, this is labeled 1, this is 1, this is 2, this is 1 and so on. So, you can imagine that this would be 2, this would be 1 and this would be 1. This edge is labeled 2. So, I think here we have labeled every single edge belonging to this graph. The purpose of labeling the edges is that we are prioritizing certain edges over the others. An edge which is labeled 1 will be taken before an edge labeled 2. That is, when this vertex is visited, the first edge that is taken by the DFS is going to be the edge which is labeled 1 out of this vertex. Only after all the searches that are accessible from that vertex are finished will the DFS come back to this node and then trace the edge which is labeled 2 if the destination vertex has not been visited yet. So, that is the purpose of labeling the edges in this fashion. Now, how do we achieve the reduction now? This reduction is going to be claimed using a theorem. We want to claim that for all I, if Gi evaluates to 1, then DFS of S of I is less than DFS of T of I, and in Gi the path taken by the DFS is from enter of I to S of I, down the stairs to T of I to exit of I. In this picture, the path that we are talking about will be starting at enter of I, traveling through B1 of I, B2 of I and then coming to S of I, and then going down the path labeled 1 and then through the edge labeled 2 to I of A1 and then out through the edge labeled 1 and then to I of A2 and so on. I of A1, I of A2 etc. will be visited in turn. So, this will create the impression of taking the stairs downwards until we reach the vertex Ti and then we exit through exit of I. In other words, we will be traveling in this manner. The path taken would be like this if G of I evaluates to 1. The statement is not complete, and if G of I evaluates to 0, which is the other possibility, then DFS of T of I will turn out to be less than DFS of S of I, which means T of I will be visited before S of I, and as opposed to the previous case, in Gi the path taken by the DFS will be different now. It will start from enter of I within G of I, go to T of I and then through the lift up to S of I and then to exit of I. Going back to the figure once again, starting at enter of I, we would take the edge labeled 2 to come to T of I. From T of I, we take the edge which is labeled 1 to go up. From there again, we will take the edge which is labeled 1 to go up, and so on, going all the way up to S of I. This going up is what I termed taking the lift upwards. So, from T of I to S of I, we take the lift upwards, traveling through the straight edges until we reach S of I. After that, we take the edge which is labeled 2 to come to exit of I and then get out. So, in this case, the path traced would be like this. So, once again, the claim that we make is this: for every I, if Gi evaluates to 1, then Si will be visited before T of I, and if Gi evaluates to 0, then T of I will be visited before S of I by the DFS. And moreover, if G of I evaluates to 1, the path taken by the DFS in Gi would look like this one. On the other hand, if Gi evaluates to 0, the path taken within Gi by the DFS would look like this. So, this is our claim. So, we shall prove this by induction. For basis, let us consider I equal to 1. G1 has to be an input of value 1. Therefore, according to our claim, for our claim to be true, we should have a path of this sort traced within G1. So, let us see how would the DFS go within G1. So, G1 is an instance of this I replaced by 1. So, the DFS will begin with enter 1. There is only one way for the DFS to go, which is to S of 1, and from there is only one way to go. From there it will go to I of A1. At I of A1, the DFS will naturally take the edge which is labeled 1, so it climbs down, and then again there is only one way to go, which is to I of A2. From there again it will take the edge which is labeled 1, and so on. It takes the stairs downwards until it reaches T of I. There is no other way for the DFS to explore. The DFS must necessarily travel through this, because all these edges with labels have labels 1. So, from T of I, it will go to exit of I and then come out of G1. So, all the vertices of G1 would be visited in this manner. Therefore, the statement holds good. In other words, S of 1 is visited before T of 1, and the path in G1 is of this form. So, the statement holds good for I equal to 1. Now, as an induction hypothesis, let me assume that the claim is true for all the previous gates and then in the induction step I am considering the ith gate. Now, for the ith gate there are two possibilities. One is that Gi is an input of value 1. In this case, Gi is identical to G1. So is capital Gi to capital G1. Therefore, DFS will proceed exactly as it did in G1, and therefore, path that we obtain is of this sort, and S of I will be visited before T of I. And in particular, Gi evaluates to 1, therefore, the claim holds good. On the other hand, if G of I happens to be the NOR of two gates GB1 and GB2, then let us see. Then there are various possibilities. The first of the possibilities is that GB1 and GB2 both evaluate to 0. Therefore, by induction hypothesis, in GB1 and GB2, the paths taken were of this form. Just we had a path of this form in both GB1 and GB2. Now, imagine the graph GB1. In GB1, B1I was a vertex on the right hand side like this. In GB1, this is Gi. Instead, if you imagine GB1 here, I is a vertex that is to come later. Therefore, I is a gate which will use the output of GB1. Therefore, the vertex B1I would appear on the right side. Now, we know that GB1 evaluated to 0. Therefore, in GB1, the path taken was from enter 1 to T of I and then up through the lift, out through exit I, which means all these vertices on the right hand side had not been visited, which means in particular all the edges which are labeled 1 out of these vertices on the right hand side have been taken, but vertices B1I has not been visited in particular, and this is indeed the case with GB2 as well. Therefore, we find that in GI, B1I and B2I are unvisited. These are unvisited vertices. Once again, going back to the figure. Now let us see how the DFS would proceed within G of I. When the DFS begins at enter of I, it tends to take the edge which is labeled 1, it explores along the edge labeled 1, it comes to B1I. B1I has not been visited before. Therefore, it will take the edge which is labeled 2 out of this. So, when you come to B1I, it would explore the edge which is labeled 1 out of B1I, but this takes us to a vertex which has already been visited in GB1. Therefore, we backtrack, come back to B1I and take the edge which is labeled 2. So, we have now reached B2 of I, B2I, but B2I had not been visited before. Therefore, we visit B2I, there is no backtracking, and then we consider the edge which is labeled 1 out of B2I, which again takes us to a vertex that is visited before in GB2. Therefore, we backtrack, come to B2I, and we proceed to S of I. Once we are at Si, we take the edge labeled 1 to go down the line. From there, the edge which is labeled 1 is going backwards. That vertex has already been visited, that is vertex Si has already been visited. Therefore, we would be going to IA1. From there, we would take the edge which is labeled 1 to come to the vertex on the right side, which from there again vertex 1 edge labeled 1 is taking us back to the vertex which has already been visited. So, we would be taking the edge which is labeled 2 to come to IA2, and we continue in this fashion visiting IA1, IA2, IA3 etc. in turn until we come to IAK. Once we are at IAK, again we take the edge which is labeled 1, we come to TI. Once we are at TI, the edge which is labeled 1 is taking us backwards to a vertex which is already visited. So, we do not take this edge, we backtrack to TI and take the edge which is labeled 2, that will take us to exit of I. So, what we find is that the path that the DFS traces is from enter I to B1I to B2I to S of I, and then through IA1, IA2 through IAK, then TI and then exit I. This is exactly what the claim was. Since B1I and B2I were unvisited, we were allowed to move along the path, and therefore, in GI we trace a path of this form, which is exactly according to the claim. This is the sort of a path that we trace within GI, and then obviously S of I is visited before T of I. DFS of S of I is less than the DFS of T of I. So, in this case the claim holds good. Now, let us consider the second case. In this case, let us say GB1 equal to 1 or GB2 equal to 1. At least one of them is 1. Then GI evaluates to 0. GI happens to be the NOR of these two, GB1 and GB2. GI evaluates to 0. What this means is that when we visited one of the two graphs GB1 and GB2, we had taken this path where S of B1 came before T of B1. That is, if GB1 had a value of 1. On the other hand, if GB2 had a value of 1, then we would have done the same in GB2. So, in at least one of the two graphs, we had taken this path. Now, what does it entail? It means that the rightmost vertices had all been visited. Among them would have been either B1I or B2I. So, at least one of these two vertices B1I and B2I have been visited before. Therefore, when DFS starts at enter I here now, what happens is this: it proceeds to B1I. If B1I had not been visited before, then we would proceed to B2I, but then we know that at least one of them has been visited. So, at one of these vertices we will backtrack, we will not be allowed to proceed further. So, we backtrack all the way to enter I. Once we are back at enter I, we attempt a search through the next available edge, which is the edge that is labeled 2, that will take us to Ti. Ti has not been visited before, but once we are at Ti, we trace the edge which is labeled 1, that will take us up. So, we are now taking the lift upwards. At each of these vertices we take the edge that is labeled 1. So, these edges will take us up to Si through the lift. Once we are at Si, the edge which is labeled 1 is taking us back to a vertex that is already visited. Therefore, we should make an attempt through the edge which is labeled 2, that will take us to exit I. Now, we go out of graph Gi. So, what we find is that the path traced happens to be in Gi. In Gi, we take a path of this sort. This is enter of I and this is exit of I. But in this case, this vertex T of I is visited before S of I. That is precisely what the claim was, that T of I is visited before S of I, or DFS T of I is less than DFS S of I. So, once again the claim holds good. So, that completes the induction, therefore, the claim is true. Once the claim is true, we can apply the claim to Gn. Therefore, we find that in Gn, vertex Sn is visited before vertex Tn precisely when gate Gn evaluates to 1. Now, that is precisely our problem was with NOR CVP. We were given the circuit and we wanted to check whether Gn evaluates to 2 or not. Does Gn evaluate to 1? This was our question. What we find is that this happens if and only if DFS of S of n is less than DFS of T of n. But this relation can be checked by invoking ODFS on the graph with 3 particular vertices. These are enter 1, the DFS must begin with enter 1, and then S of n and T of n. If this is affirmative, then Gn evaluates to 1. So, the NC reduction that we are talking about involves this. Given an instance of the NOR CVP circuit, we construct the graph G in this manner and then invoke ODFS on this graph. But then how do you construct the graph? Constructing of the graph requires establishing sequences of certain sort. We have to establish sequences of vertices of this sort. But then you know all this can be done in polylogarithmic time using a polynomial number of processors. Therefore, setting up of the graph is indeed an NC work. So, that establishes that the problem of NOR CVP can be reduced to ODFS. That completes the second part of the proof. Therefore, putting the 2 parts, we know that ODFS is P complete for NC reductions, which is a bit of a setback because DFS is one of the most elementary sequential algorithms and forms a subroutine to many algorithms, but here we find that DFS is not easily parallelizable. So, in the parallel setting, DFS is not an easy problem. In the next class, we shall show that the max flow problem is P complete for NC reductions as well. Therefore, we cannot expect to have efficient parallelization for that problem as well. That is it from this lecture. Hope to see you in the next. Thank you.